Bismillah Rahman Rahim. Assalamu alaikum. Electricity is one of the major energy source used for industries and houses to enable lighting systems, air conditioning system, to run the machineries, and to use all of electrical and electronic home appliances. Stages of electrical network system. 1. Generation/power plants. 2. Transmission network. 3. Distribution network. Power sector in Saudi Arabia. Saudi Arabia is a large country with an area of 2.3 million square kilometers. The Saudi Electric Company, SEC, is responsible for generating and distributing electricity in the kingdom. The power grid system is massive, supplying electricity to approximately 80% of the population. With an electricity distribution network that extends to cities, towns and villages across the country, its network consists of 8,750 miles of transmission lines, 52,000 miles of distribution lines and over 53,000 miles of service connections. In the more remote, sparsely populated regions of the kingdom, it is uneconomical to extend grid access, and as a result these areas tend to rely on independent/off-grid sources for electricity. The country currently utilizes a dual-voltage power distribution system. In residential and light commercial buildings, the kingdom uses 127 volts, whereas 220 volts is required for larger commercial and industrial applications. With more than 70% of the world now using a 23400-volt distribution system, the government approved plans in August 2010 to move the country to a 23400-volt system. The change to the new voltage in the existing areas will take place within period of 25 years from the date of the resolution's effective date. This period is divided into two stages, a preparatory stage of 10 years and 15 years implementation stage. Electricity generations. Electricity produced in multiple ways from other form energy to electrical energy as listed below. Electricity generation is the process of generating electric power from sources of primary energy. For electric utilities in the electric power industry, it is the first stage in the delivery of electricity to end users, the other stages being transmission, distribution, energy storage and recovery, using pumped storage methods. A characteristic of electricity is that it is not a primary energy freely present in nature in remarkable amounts. Electricity generated at a power station by electromechanical generators, primarily driven by heat engines fueled by combustion or nuclear fission, but also by other means such as the kinetic energy of flowing water and wind. Other energy sources include solar photovoltaics and geothermal power. 1. Thermal power plants. A. Pulverized coal-fired power generation. Pulverized coal-fired power generation is currently the major method of coal-fired power generation. Coal pulverized to fine powder and burned in the boiler. Heat in. The boiler boils the water into steam. The steam pressure turns the steam turbine and the generator generates electricity. B. Combined cycle power generation. A combined cycle power first generates gas by burning fuel in the compressed air. Pressure of the gas rotates the gas turbine and the generator creates electricity. Moreover, exhaust heat from gas turbine utilized for boiling water to generate steam, which rotates turbine to generate. C. Integrated coal gasification combined cycle, IGCC. Integrated coal gasification combined cycle, IGCC, gasifies the fuel coal in the gasifier. Gasified fuel is burnt in the compressed air to generate gas. Pressure of the gas rotates the gas turbine to generate electricity. Furthermore, the exhaust gas heat from gas turbine is utilized to boil water into steam to generate electricity. 2. Nuclear/atomic power plants. D. Boiling water reactor, BWR. Light water means normal water, opposite to heavy water. Heat produced by nuclear fission in the reactor core, and then causes the water to boil, producing steam. The steam rotate the turbine to generate electricity, then is cooled in the condenser by seawater and converted back to liquid water. This water then returned to the reactor core. E. Pressurized water reactor, PWR. Light water means normal water, opposite to heavy water. Heat is produced by nuclear fission in the reactor core, but heated water is suppressed before boiling by applying a high pressure. This water with high temperature and pressure is sent to the steam generator, boils the water into steam, and then rotates the turbine to generate electricity in the generator. After that it is cooled in the condenser by seawater and converted back to liquid water. This water then returned to the steam turbine. 3. Hydropower plants. A. Conventional, dams. Most hydroelectric power comes from the potential energy of dammed water driving a water turbine and generator. The power extracted from the water depends on the volume and on the difference in height between the source and the water's outflow. This height difference is called the head. A large pipe, the penstock, delivers water from the reservoir to the turbine. B. Pumped storage. This method produces electricity to supply high peak demands by moving water between reservoirs at different elevations. At times of low electrical demand, the excess generation capacity is used to pump water into the higher reservoir. When the demand becomes greater, water is released back into the lower reservoir through a turbine. Pumped storage schemes currently provide the most commercially important means of large-scale grid energy storage and improve the daily capacity factor of the generation system. C. Run-of-the-river. Run-of-the-river hydroelectric stations are those with small or no reservoir capacity, so that only the water coming from upstream is available for generation at that moment, and any oversupply must pass unused. A constant supply of water from a lake or existing reservoir upstream is a significant advantage in choosing sites for run-of-the-river. D. Tide. A tidal power station makes use of the daily rise and fall of ocean water due to tides. Such sources are highly predictable, and if conditions permit, construction of reservoirs can be dispatch-able to generate power during high demand periods. 4. Wind power plants. Wind power is the use of airflow through wind turbines to mechanically power generators for electricity. Wind power, as an alternative to burning fossil fuels, is plentiful, renewable, widely distributed, clean, produces no greenhouse gas emissions during operation, consumes no water, and uses little land. 5. Solar power plants. Solar power is the conversion of energy from sunlight into electricity, either directly using photovoltaics, PV, indirectly using concentrated solar power, or a combination. Concentrated solar power systems use lenses or mirrors and tracking systems to focus a large area of sunlight into a small beam. Photovoltaic cells convert light into an electric current using the photovoltaic effect. 6. Geothermal power plants. Geothermal energy is thermal energy generated and stored in the earth. Thermal energy is the energy that determines the temperature of matter. The geothermal energy of the Earth's crust originates from the original formation of the planet and from radioactive decay of materials. This geothermal heat used to run thermal turbines to produce electricity. 7. Turbines. In most type of power plants, turbines are used to drive generators as depicted below. A turbine is a rotary mechanical device that extracts energy from a fluid flow/steam flow and converts it into useful work. The work produced by a turbine can be used for generating electrical power when combined with a generator. Transmission network. As the first stage is power generation, the next stage will be transmission of power through high-tension towers, and the purpose of this network is to transmit the generated high voltage until the grid station. The network from power plants to grid stations are called transmission network, and all assets/utilities used in this network called transmission utilities. National Grid SA works to regularly improve and develop transmission networks. 110. 380 kV in all sectors of the Saudi Electricity Company, Central, East, West and South. In addition, SEC have some ultra-high voltage projects, 230 to 380 kV. Transmission lines are sets of wires, called conductors, that carry electric power from generating plants to the substations that deliver power to customers. At a generating plant, electric power is stepped up to several thousand volts by a transformer and delivered to the transmission line. The type of transmission structure is determined by the characteristics of the transmission line's route, including terrain and existing infrastructure. Most transmission lines are high-voltage three-phase alternating current, AC, although single-phase AC is sometimes used in railway electrification systems. High-voltage direct current, HVDC, technology is used for greater efficiency over very long distances, typically hundreds of miles. HVDC technology is also used in submarine power cables, typically longer than 30 miles, 50 kilometers, and in the interchange of power between grids that are not mutually synchronized. HVDC links are used to stabilize large power distribution networks where sudden new loads, or blackouts, in one part of a network can result in synchronization problems and cascading failures. Electricity is transmitted at high voltages, 115 kV or above, to reduce the energy loss, which occurs in long-distance transmission. Power usually transmitted through overhead power lines. Underground power transmission has a significantly higher installation cost and greater operational limitations, but reduced maintenance costs. Underground transmission sometimes used in urban areas or environmentally sensitive locations. Stages of electricity flow. Distribution network. Electrical distribution network starts from the grid stations, and the purpose of this entire distribution network is to provide low-voltage power supply to the houses and to supply the medium-voltage direct power supply to the large customers such as small industries, shopping complexes, and others. This entire network consists of multiple electrical utilities/assets involved to distribute the electricity, mainly in substations. Transformers step down the power to a lower voltage and deliver it to distribution lines. Distribution lines carry power to farms, homes, and businesses. We will have the detailed information about every asset as described below. Electrical distribution network in GIS. Electrical distribution network with all the assets and network cables mapped in ESRI file geodatabase by using the standard UDM, Unified Data Model, used by Saudi Electricity Company. All distribution network utilities and their electrical and GIS functions are explained below. 1. Station. Station is the origin of the distribution network, and it consists multiple components inside to step down the transmission power to distribution power. Mainly the step down transformers available in the grid station convert the high voltage, 110 to 460 kV, to transmission voltage 33 kV/13.8 kV. High voltage busbar to connect with both high voltage, which acts as bus sections at the secondary side of the transformer connected to distribution busbar, along with measuring units, which consists of current transformers and voltage transformers. In the grid station, power distribution converted into multiple feeders which will be providing supply to series of substations of distribution network. A typical single line diagram of station. GIS configuration of station. In GIS, a station created with all its internal components as an internal template and used with appropriate voltage and technical specification changes in the attributes of that particular station. We have used two feature classes, FCL_station and FCL_station_area, to represent the station and placed internal templates as per the internal templates defined for the project. We have filled only the surveyed attributes to this feature classes and remaining kept as null as we have not received WMS/SAP data. We have the following subtypes in station as per SEC. BSP/primary substation. Grid station. Semi-primary. Primary. Primary substation. In GIS, the station locations are represented as depicted above. We use a FCL_station point and FCL_station area and their internal components such as transformers, busbar, plant schema cables, dynamic protective devices, circuit Breakers. Most of the time the secondary voltage level is 13.8 kV, in some cases we have 33 kV as secondary. In those grid stations the primary voltages also differs from normal 33 kV. From the secondary busbar the feeders will be connecting to the series of substations based on the load and the locality of the consumers. GIS attributes for station. We have to collect the following listed attributes for station from survey field, and some attributes should be transferred from SEC mainframe/WMS/SAP database. Survey photos and attributes collected for station. Name board of the station. Overview of a grid 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 station. Station name board. 2. Substation. A distribution substation transfers power from the medium voltage to the usable low voltage system of an area. It is uneconomical to directly connecting the consumers to the main transmission network, unless they use large amounts of power. Therefore, the distribution substation reduces voltage to a level suitable for low voltage that used by all the equipment inside the houses, shops, commercial malls, etc. A typical single-line diagram of substation. A typical substation's layout diagram. GIS configuration of substation. We have multiple types of substations described by their construction and usages. Following are the type of substations available in SEC. Unit substation. Package unit substation. Room substation. Pole-mounted substation. Platform substation. Switching substation. Ground-mounted TX. Streetlight substation. We have used two feature classes FCL_substation and FCL_substation_area to represent the substation and placed internal templates as per the internal templates defined for the project. Room, unit, package substations internal templates placed inside the 4 points surveyed and aligned with road centerline where possible. Wherever 2 points surveyed, we have aligned the template to the line of both the points surveyed. Substation points are retained at the original location of poles for PMT substation. Substation points placed inside the substation area polygon for room, unit and package substations. We have used 2 by 2 meter sized area for PMT substations to match with ground reality and MV cable connected through external cutout fuse. We have used T-joints to branch the cable from MV line to PMT substation. We have used LVDB_area polygon with single LV circuit breaker point when there is single breaker used to connect the LV circuit in the pole-mounted substation. A. Unit substation. Unit substations are mostly available in the open places and covered by safety pillars or safety walls as depicted below. These type of SS will contain transformer, LVDP and switchgear in the same location. Overview of Unit SS. GIS attributes for substation. We have to collect the following listed attributes for station from survey field, and some attributes should be transferred from SEC mainframe/WMS/SAP database. GIS configuration of unit substation. We have used many types of unit substation template according to survey in our project. By using total number of circuits in LVDB, type of protection in LVDB, switchgear, subtypes and transformer rated voltages and few other parameters. Below mentioned are few example of templates for unit SS. We have used the below depicted template when LVDB has 12 circuits with circuit breaker as protection, transformer has 13.8 kV primary voltage and 3-way switchgear. We have used the below depicted template when LVDB has 8 circuits with circuit breaker as protection, transformer has 13.8 kV primary voltage and 3-way switchgear. We have used the below depicted template when LVDB has 6 circuits with circuit breaker as protection, transformer has 13.8 kV primary voltage and 3-way switchgear. We have used the below depicted template when LVDB has 4 circuits with circuit breaker as protection, transformer has 13.8 kV primary voltage and 3-way switchgear. We have used the below depicted template when LVDB has 2 circuits with circuit Breaker as protection, transformer has 13.8 kV primary voltage and 3-way switchgear. We have used the below depicted template, when LVDB has 12 circuits with fuse as protection, transformer has 13.8 kV primary voltage and 3-way switchgear. We have used the below depicted template, when LVDB has 8 circuits with fuse as protection, transformer has 13.8 kV primary voltage and 3-way switchgear. We have used the below depicted template, when LVDB has 6 circuits with fuse as protection, transformer has 13.8 kV primary voltage and 3-way switchgear. We have used the below depicted template, when LVDB has 4 circuits with fuse as protection, transformer has 13.8 kV primary voltage and 3-way switchgear. We have used the below depicted template, when LVDB has 2 circuits with fuse as protection, transformer has 13.8 kV primary voltage and 3-way switchgear. B. Package unit substation. A package substation contains its all components packed inside a rectangular steel cage, in which includes transformer, switchgear, and LV distribution panel. Overview of package unit SS. Overview of package unit SS. Transformer inside package unit SS. Switchgear inside package unit SS. LVDB inside package unit SS. We have used many types of package substation template according to survey in our project by using total number of circuits in LVDB, type of protection in LVDB, switchgear, subtypes and transformer rated voltages and few other parameters. Below mentioned are few example of templates for unit SS. We have used the below depicted template, when LVDB has 12 circuits with circuit breaker as protection, transformer has 13.8 kV primary voltage and 3-way switchgear. We have used the below depicted template, when LVDB has 8 circuits with circuit breaker as protection, transformer has 13.8 kV primary voltage and 3-way switchgear. We have used the below depicted template, when LVDB has 6 circuits with circuit breaker as protection, transformer has 13.8 kV primary voltage and 3-way switchgear. We have used the below depicted template, when LVDB has 4 circuits with circuit breaker as protection, transformer has 13.8 kV primary voltage and 3-way switchgear. We have used the below depicted template, when LVDB has 2 circuits with circuit breaker as protection, transformer has 13.8 kV primary voltage and 3-way switchgear. We have used the below depicted template, when LVDB has 12 circuits with fuse as protection, transformer has 13.8 kV primary voltage and 3-way switchgear. We have used the below depicted template, when LVDB has 8 circuits with fuse as protection, transformer has 13.8 kV primary voltage and 3-way switchgear. We have used the below depicted template, when LVDB has 6 circuits with fuse as protection, transformer has 13.8 kV primary voltage and 3. We have used the below depicted template, when LVDB has 4 circuits with fuse as protection, transformer has 13.8 kV primary voltage and 3-way switchgear. We have used the below depicted template, when LVDB has 2 circuits with fuse as protection, transformer has 13.8 kV primary voltage and 3-way switchgear. C. Room substation. Room substations are inside a room or space in a building dedicated to electrical equipment installation that includes the terminations of the transmission/distribution lines and switchgear, and include transformers, LVDB. The substation also typically includes all the necessary devices for control and protection. Overview of Room SS. Overview and inside the Room SS. Inside the Room SS. We have used many types of room substation template according to survey in our project. By using total number of circuits in LVDB, type of protection in LVDB, switchgear, subtypes and transformer rated voltages and few other parameters. Below mentioned are few example of templates for Room SS. We have used the below depicted template, when LVDB has 12 circuits with circuit breaker as protection, transformer has 13.8 kV primary voltage and 3-way switchgear. We have used the below depicted template, when 5 LVDB has individual circuits with Circuit breaker as protection. Transformer has 13.8 kV primary voltage and 3-way. Switchgear. We have used the below depicted template, when LVDB has 4 circuits with circuit breaker as protection. Transformer has 13.8 kV primary voltage and 3-way switchgear. We have used the below depicted template, when LVDB has 3 circuits with circuit breaker as protection. Transformer has 13.8 kV primary voltage and 3-way switchgear. We have used the below depicted template, when LVDB has 8 circuits with circuit breaker as protection. Transformer has 13.8 kV primary voltage and 3-way switchgear. We have used the below depicted template, when LVDB has 12 circuits with fuse as protection. Transformer has 13.8 kV primary voltage and 3-way switchgear. We have used the below depicted template, when LVDB has 8 circuits with fuse as protection. Transformer has 13.8 kV primary voltage and 3-way switchgear. We have used the below depicted template, when LVDB has 12 circuits with fuse as protection. Transformer has 13.8 kV primary voltage and 3-way switchgear with 3-leg EOS. We have used the below depicted template, when 2 LVDB has 12 circuits with fuse as protection. Transformer has 13.8 kV primary voltage and 3-way 2 switchgear. D. Pole-mounted substation. Pole-mounted substation are used only for sub-distribution of the low-voltage form. August 13, 33 kV to an individual customer or for multiple household customers. Usually all. The equipment of the substation mounted/fixed in a pole structure, mostly on H-poles. Even we can find some low-weight transformers mounted in a single pole as well. We have used many types of pole-mounted substation template according to survey in our project by using total number of circuits in LVDB, type of protection in LVDB and transformer rated voltages and few other parameters. Below mentioned are few example of templates for pole-mounted SS. We have used the below depicted template, when LVDB has 1 circuit with fuse as protection. Transformer has 13.8 kV primary voltage. We have used the below depicted template, when LVDB has 2 circuits with fuse as protection. Transformer has 13.8 kV primary voltage. We have used the below depicted template, when LVDB has 4 circuits with fuse as protection. Transformer has 13.8 kV primary voltage. We have used the below depicted template, when LVDB has 6 circuits with fuse as protection. Transformer has 13.8 kV primary voltage. We have used the below depicted template, when LVDB has 8 circuits with fuse as protection. Transformer has 13.8 kV primary voltage. We have used the below depicted template, when 2 LVDB has 2 circuits each with fuse as protection. Transformer has 13.8 kV primary voltage. We have used the below depicted template, when 2 LVDB has 1 circuit each with fuse as protection. Transformer has 13.8 kV primary voltage. We have used the below depicted template, when 3 LVDB has 1 circuit each with fuse as protection. Transformer has 13.8 kV primary voltage. We have used the below depicted template, when 2 LVDB has 1 circuit and 2 circuits each with fuse as protection. Transformer has 13.8 kV primary voltage. We have used the below depicted template, when 2 LVDB has 1 circuit each with CB as protection and 1 LVDB with 8 fuse as protection. Transformer has 13.8 kV primary voltage. We have used the below depicted template, when LVDB has 1 circuit with circuit breaker as protection. Transformer has 13.8 kV primary voltage. We have used the below depicted template, when 2 LVDB has 1 circuit each with circuit breaker as protection. Transformer has 13.8 kV primary voltage. We have used the below depicted template, when LVDB has 2 circuits with circuit breaker as protection. Transformer has 13.8 kV primary voltage. We have used the below depicted template, when 3 LVDB has 1 circuit each with circuit breaker as protection. Transformer has 13.8 kV primary voltage. We have used the below depicted template, when LVDB has 3 circuits with circuit breaker as protection. Transformer has 13.8 kV primary voltage. We have used the below depicted template when LVDB has 4 circuits with circuit breaker as protection. Transformer has 13.8 kV primary voltage. We have used the below depicted template when LVDB has 6 circuits with circuit breaker as protection. Transformer has 13.8 kV primary voltage. We have used the below depicted template when 2 LVDB has 1 circuit and 2 circuits each with circuit breaker as protection. Transformer has 13.8 kV primary voltage. We have used the below depicted template when 2 LVDB has 2 circuits each with circuit breaker as protection. Transformer has 13.8 kV primary voltage. We have used the below depicted template when 2 LVDB has 2 fuse for 1 LVDB and 1 circuit breaker as protection for 1 LVDB. Transformer has 13.8 kV primary voltage. We have used the below depicted template when 3 LVDB has 1 fuse for 1 LVDB and 1 circuit breaker each as protection for 2 LVDB. Transformer has 13.8 kV primary voltage. We have used the below depicted template when 3 LVDB has 2 fuse for 1 LVDB and 1 circuit breaker each as protection for 2 LVDB. Transformer has 13.8 kV primary voltage. Platform substation. Platform substations are usually constructed inside the city areas where all substation equipment installed in a concrete platform with the support of a small poles as depicted in the below screenshot. We did not find any platform substations in our project area, but you can find many platform substation in Riyadh City. Switching substation. Switching stations constructed only for the purposes of switching the feeders when there are any blackout in feeders. Most of the time these switching stations are inside grid stations only. Overview of a switching station. Ground-mounted TX. Unit ground-mounted TX are rarely found, as in this case is only transformers are mounted on the ground without any other substation components such as LVDB, switchgears. Usually these kind of transformers placed inside the industrial areas. Street light substation. Unit transforms voltage from medium to low, substation components, LVDB and transformer. Main function is connecting to CT meters and street lights. We have used many types of street light substation template according to survey in our project by using total number of circuits in LVDB, type of protection in LVDB and transformer rated voltages and few other parameters. Below mentioned are few example of templates for street light SS. We have used the below depicted template when LVDB has 1 circuit with fuse as protection. Transformer has 13.8 kV primary voltage. We have used the below depicted template when LVDB has 1 circuit with circuit breaker as protection. Transformer has 13.8 kV primary voltage. We have used the below depicted template when LVDB has 2 circuits with virtual back to back as protection. Transformer has 13.8 kV primary voltage. We have used the below depicted template when LVDB has 2 circuits with circuit breaker as protection. Transformer has 13.8 kV primary voltage. We have used the below depicted template when LVDB has 4 circuits with circuit breaker as protection. Transformer has 13.8 kV primary voltage. We have used the below depicted template when 2 LVDB has 2 circuits each with circuit breaker as protection. Transformer has 13.8 kV primary voltage. We have used the below depicted template when LVDB has 8 circuits with fuse as protection. Transformer has 13.8 kV primar. We have used the below depicted template when LVDB has 8 circuits with circuit breaker as protection. Transformer has 13.8 kV primary voltage. Switchgear. Switchgear is part of substation and it function as same as RMU, but these switchgears are equipped and installed inside room substations, unit substation, or part of package substations. In an electric power system, switchgear is the combination of electrical disconnect switches, fuses or circuit breakers used to control, protect, and isolate electrical equipment. Switchgear used to energize and de-energize equipment to allow maintenance work done and to clear faults downstream. Switchgear unit used in secondary, MV, distribution system and is sealed with vacuum or SF6 gas. It protects the secondary transformer from transients either from load or source side. A typical single-line diagram of switchgear. GIS configuration of switchgear. We have the below depicted internal template configurations for switchgear with the combination of switches, busbar, and plant schema cables. In switchgear always operates in medium voltages only, and it acts as connection agent between the substations to substations along with RMU, EOS, and other distribution equipment. The position of the switchgear maintained as per the ground reality wherever possible and in few locations. We kept as per template itself to maintain the consistency. We have two subtypes in switchgears as per SEC, and we always used only switchgear as subtype in our project. Switchgear. Switchgear, MF. GIS attributes for switchgear. We have to collect the following listed attributes for station from survey field, and some attributes should be transferred from SEC mainframe/WMS/SAP database. SL, #attribute requirement. Captured from attribute description. Survey photos and attributes collected for switchgear. Overview of switchgear. Nameplate of switchgear. 4. Transformer. A transformer is a static electrical device that transfers electrical energy between two or more circuits through electromagnetic induction. A varying current in one coil of the transformer produces a varying magnetic field, which in turn induces a varying electromotive force, EMF, or voltage, in a second coil. Power transferred between the two coils, without a metallic connection between the two circuits. Transformers used to increase or decrease the alternating voltages in electric power. Applications. A typical transformer layout diagram. GIS configuration. Transformer is a simple point representation in GIS as part of substation internal templates as depicted below. Transformers of PMT substations moved from their original surveyed position as part of internal. In common, we have used the available domain values for voltages as per the standards and added 400 volts wherever appropriate into the domains as per the change request shared. When the transformer output voltage is 13.8/400/231, we use domain 2 of 13.8/0.4 kV. When the transformer output voltage is 13.8/231/133, we use domain 1 of 13.8/0.231 kV. We have the following list of transformer subtypes in our project based on their primary and secondary voltage, and we have used appropriate subtypes as per nameplate details. 33 kV, 13.8 kV transformer. 13.8 kV, LV transformer. 33 kV, LV transformer. Consumer transformer. Auxiliary transformer. 69 kV, 13.8 kV transformer. 132 kV, 33 kV transformer. 132 kV, 13.8 kV transformer. 69 kV, 33 kV transformer. 11 kV, LV transformer. 13.8 kV transformer. 34.5 kV, 11 kV transformer. 34.5 kV, LV transformer. 11 kV, LVOH transformer. 13.8 kV, LVOH transformer. 33 kV, LVOH transformer. 34.5 kV, LVOH transformer. 34.5 kV, 13.8 kV transformer. GIS attributes for transformer. We have to collect the following listed attributes for station from survey field, and some attributes should be transferred from SEC mainframe/WMS/SAP database. Survey photos and attributes collected for transformer. Overview picture of substation transformer. Transformer nameplate picture. Overview picture of substation transformer. Transformer nameplate picture. Overview of pole-mounted substation transformer. Transformer nameplate picture. Overview of package unit SS transformer switchgear. Transformer nameplate. Overview of unit substation transformer. Transformer nameplate picture. Overview of room substation with transformer. Transformer nameplate picture. 5. Low voltage distribution panel, LVDB. A distribution board is a component of an electricity supply system that divides an electrical power feed into subsidiary circuits while providing a protective fuse or circuit breaker for each circuit in a common enclosure. The main purpose of these LVDB are to distribute the low voltage into multiple circuits, and further these circuits connected to mini-pillars or directly connected to the individual customers. A typical single-line diagram of LVDB. GIS configuration of LVDB. We represented polygons as LVDB carries their original attributes from the survey field. When there are multiple LVDB boxes in a single substation represented as per the quantity of the LVDB available. We have the following subtypes in LVDB as per SEC. LVDB, LVDB, MF, MCCB. Others. GIS attributes for LVDB_area. We have to collect the following listed attributes for station from survey field, and some attributes should be transferred from SEC mainframe/WMS/SAP database. Survey photos and attributes collected for LVDB_area. Attributes from LVDB. LVDB nameplate. LVDB in a pole-mounted SS with breaker. LVDB in a pole-mounted SS with fuse. LVDB in a pole-mounted SS with multiple MCCB. 6. Ring main unit. A ring main unit, RMU, is a totally sealed, gas-insulated compact switchgear unit. The primary switching devices can be either switch disconnectors or fused switch disconnectors or circuit breakers. Typical RMU. How RMU works in a distribution network. GIS configuration of RMU. All RMUs are represented with the below depicted configuration as internal templates, which includes busbar, planned schema cables, switches with proper connectivity. Ring main unit represented by using the feature classes FCL_RMU and FCL_RMU_area by using the configuration of switches and respective attribute details filled in the RMU point. We have following subtypes in RMU as per SEC. RMU 3-way, RMU 4-way, RMU 3-way, RMU 4-way, RMU. GIS attributes for RMU. We have to collect the following listed attributes for station from survey field, and some attributes should be transferred from SEC mainframe/WMS/SAP database. Survey photos and attributes collected for RMU. RMU inside room. RMU open photograph. RMU nameplate. 7. Extensible oil switch, EOS. Extensible oil switch, EOS, is a device for adding additional feeder from the MV network. For proving new added load due to urban development and as per load increase. Development in a specific area. These extensible oil switches are used to provide power supply and breaking the connection in an electric circuit. Usually there are multiple oil switches connected in series to make multiple branches from a single feeder. We have used EOS_area and FCL_extensible to represent EOS and relevant attribution done according to the requirements spreadsheet attached in the supporting documents. Typical EOS SLD of EOS. GIS configuration of EOS. EOS are configured as depicted below using busbar, plant schema, extensible point to represent the connectivity inside the EOS. We have the following subtypes in extensible. Extensible. GIS attributes for EOS. We have to collect the following listed attributes for station from survey field, and some attributes should be transferred from SEC mainframe/WMS/SAP database. Survey photos and attributes collected for EOS. EOS nameplate. 8. Distribution box. Distribution box is used to divide the low voltage from LVDB or coming directly from SS to houses as usable low voltage. Majorly we have mini pillars and service boxes in our project area. Mini pillars further segregated into two types based on their manufactured material as fiber or steel. Below are typical mini pillar boxes available in Saudi Arabia. GIS configuration of distribution box. We have used the layers FCL_DISTRIBUTIONBOX and FCL_distribution_area to represent the mini pillars in GIS. As instructed by SEC, we have placed the mini pillar internals with 0.2 meter gap from the parcel boundary and aligned to the parcels. We have kept the distribution box point feature at the original surveyed location itself to make sure the survey accuracy been maintained throughout the office. Hence there are many distribution box area polygons are isolated from the distribution box points. We have attributed the circuit details by using the photographs only. We have following types of distribution boxes: mini pillar, low voltage distribution board, MCCB, service box, electric box, pedestal, template for fused type mini pillars, template for direct type mini pillars. GIS attributes for mini pillar. We have to collect the following listed attributes for station from survey field, and some attributes should be transferred from SEC mainframe/WMS/SAP database. Survey photos and attributes collected for mini pillar. Another example of mini pillars attributes. GIS attributes for other type of distribution box. We have to collect the following listed attributes for station from survey field, and some attributes should be transferred from SEC mainframe/WMS/SAP database. Survey photos and attributes collected for other distribution box. Low voltage distribution board, service box, electri. 9. Busbar. Busbar is a metallic strip or bar, typically housed inside switchgear, panel boards, and busway enclosures for local high current power distribution. They are also used to connect high voltage equipment at electrical switchyards and low voltage equipment. They are generally uninsulated and have sufficient stiffness to be supported in air by insulated pillars. These features allow sufficient cooling of the conductors and the ability to tap in at various points without creating a new joint. GIS configuration of busbar. Have used busbar inside the internal templates of substation, station, distribution boxes. Their subsequent voltages they carry during operations categorize busbar. 11 kV busbar, 13.8 kV busbar, 33 kV busbar, 34.5 kV busbar, 69 kV busbar. LV panel. Mini pillar. GIS attributes for busbar. We have to collect the following listed attributes for station from survey field, and some attributes should be transferred from SEC mainframe/WMS/SAP database. 10. Plant schema cables. Plant schema cables are used to provide internal component connections inside the substations. These cables are mostly insulated cables, which used in between component to component. GIS configuration of plant schema cables. We have the following subtypes in plant schema cable as per SEC. BSP. Grid station. High voltage. Low voltage. Medium voltage. Net level bridge. Primary. Primary substation. Road lightning. Semi-primary. Virtual line. GIS attributes for plant schema cable. We have to collect the following listed attributes for station from survey field, and some attributes should be transferred from SEC mainframe/WMS/SAP database. 11. Switch. Switch functions are connect or disconnect the electricity flow in a particular direction of the electricity distribution. We have multiple types of switches in the distribution voltage. GIS configuration of switch. Switch is represented as a simple point feature in GIS, with proper connection with linear electrical lines. We have the following subtypes in switches as per SEC. 11 kV switch. 13.8 kV load break switch. 13.8 kV overhead load break switch external. 13.8 kV switch. 13.8 kV fused switch. 13.8 kV on load isolator. 13.8 kV on load isolator external. 33 kV switch fuse switch. 34.5 kV switch. 69 kV on-load isolator. Air brake switch. Bypass switch. Disconnect solid link. Disconnect solid link external. Earthing switch. Fuse cutout. Knife switch. Load brake switch. Load brake switch external. Off-load isolators. Overhead disconnect. Overhead load brake. Recloser. Solid link. Transfer switch. Underground disconnect. Underground load brake. GIS attributes for switch. We have to collect the following listed attributes for station from survey field and some attributes should be transferred from SEC mainframe/WMS/SAP database. Survey photos and attributes collected for switch. 12. Dynamic protective device. DPD is a branch of electrical power engineering that deals with the protection of electrical power systems from faults through the isolation of faulted parts from the rest of the electrical network. The objective of a protection scheme is to keep the power system stable by isolating only the components that are under fault, whilst leaving as much of the network as possible still in operation. Thus, protection schemes must apply with very pragmatic and pessimistic approach to clearing system faults. The devices that are used to protect the power systems from faults are called protection devices. We have the following subtypes in DPD as per SEC. GIS configuration of DPD. DPD represented as a simple point feature in GIS, with proper connection with linear electrical lines. We have the following subtypes in switches as per SEC. LV circuit breaker. 11 kV circuit breaker. 13.8 kV circuit breaker. 13.8 kV circuit breaker bus section. 33 kV circuit breaker. 33 kV circuit breaker bus section. 34.5 kV circuit breaker. 69 kV circuit breaker. 69 kV circuit breaker bus section. 13.8 kV auto recloser. 33 kV auto recloser. 69 kV auto recloser. 13.8 kV sectionalizer. 33 kV sectionalizer. 69 kV sectionalizer. GIS attributes for DPD. We have to collect the following listed attributes for station from survey field and some attributes should be transferred from SEC mainframe/WMS/SAP database. Survey photos and attributes collected for DPD. 13. Fuse. A fuse is an electrical safety device that operates to provide overcurrent protection of an electrical circuit. Its essential component is a metal wire or strip that melts when too much current flows through it, thereby interrupting the current. It is a sacrificial device. Once a fuse has operated, it is an open circuit, and it must be replaced or rewired, depending on type. Fuses have been used as essential safety devices from the early days of electrical engineering. Today there are thousands of different fuse designs that have specific current and voltage ratings, breaking capacity, and response times, depending on the application. The time and current operating characteristics of fuses are chosen to provide adequate protection without needless interruption. Wiring regulations usually define a maximum fuse current rating for particular circuits. Short circuits, overloading, mismatched loads, or device failure are the prime reasons for fuse operation. GIS configuration of fuse. Fuse is represented as a simple point feature in GIS, with proper connection with linear electrical lines. We have the following subtypes in switches as per SEC. LV fuse. LV fuse external. LV fuse cutout external. LV HRC fuse. 13.8 kV BAF, buric acid. 13.8 kV fuse cutout external. 13.8 kV fuse external. 13.8 kV HRC. 13.8 kV WEF, wire expulsion. 13.8 kV we fuse. 13.8 kV we fuse external. 33 kV BAF, buric acid. 33 kV HRC. 33 kV WEF, wire expulsion. 380 V HRC. 69 kV HRC 1300. GIS attributes for fuse. We have to collect the following listed attributes for station from survey field and some. Attributes should be transferred from SEC mainframe/WMS/SAP database. Survey photos and attributes collected for fuse. 14. Capacitor bank. A capacitor bank is a group of several capacitors of the same rating that are connected in series or parallel with each other to store electrical energy. There are some specific of using capacitor bank, such as it reduces line current of the system. It improves voltage level of the load. It also reduces system losses. It improves power factor of the source current. It reduces load of the alternator. It reduces capital investment per megawatt of the load. GIS configuration of capacitor bank. Capacitor banks represented as a simple point feature in GIS, with proper connection with linear electrical lines. We have the following subtypes in capacitor bank. PF and VC capacitor. Power factor control capacitor. Voltage control capacitor. GIS attributes for capacitor bank. We have to collect the following listed attributes for station from survey field and some. Attributes should be transferred from SEC mainframe/WMS/SAP database. Survey photos and attributes collected for capacitor bank. Capacitor bank on OH overview nameplate. 15. Poles. A pole is a column or post used to support overhead power lines and various other public utilities, such as electrical cable, fiber optic cable, and related equipment such as transformers and streetlights. It can be referred to as a transmission pole, power distribution pole depending on its application. Electrical wires and cables are routed overhead on poles as an inexpensive way to keep them insulated from the ground and out of the way of people and vehicles. Poles can be made of wood, metal, concrete, or composites like fiberglass. They are used for two different types of power lines: sub-transmission lines, which carry higher voltage power between substations, and distribution lines, which distribute lower voltage power to customers. GIS configuration of poles. Poles have been represented as a simple point feature in GIS by connecting overhead network lines. Every pole should be connected with OH lines except the decommissioned ones. In addition, other equipment such as switches, fuses, joints and cable risers available on the pole are represented along with poles. When there is only one other asset, they have been captured at the point as pole, but more than one asset we have used to move them with 0.25 meter in between each asset. GIS attributes for poles. We have to collect the following listed attributes for station from survey field and some. Attributes should be transferred from SEC mainframe/WMS/SAP database. Survey photos and attributes collected for poles. (16) Cable riser. Cable risers are the physical support used to rise the underground cable to the overhead network conductor line. They are usually steel or PVC pipes in nature. Most of the time, they're tied with poles as depicted below. GIS configuration of cable riser. Cable risers are used to connect the underground network cables to overhead network lines. They have been represented as a simple point feature in GIS by connecting with both OH and UG lines. We have the following subtypes in cable riser as per SEC. Cable riser. LV cable riser. MV cable riser. GIS attributes for cable riser. We have to collect the following listed attributes for station from survey field and some attributes should be transferred from SEC mainframe/WMS/SAP database. Survey photos and attributes collected for cable riser. Joints. Joints are electrical junction created between multiple cables or electrical conductors. Usually these joints are made of a metal, which conducts the electricity and have tightly fixes the cables. Electrical joints and terminations provide the required electrical connection as well as the mechanical support and physical protection of the cable. There are different types of joints and terminations based on the function, type of cable and construction materials. The design is usually influenced by the voltage and current that the cable will carry and the operational environment. The electrical connection requirements relate to the voltage drop, current carrying capacity, compatibility of the materials, etc. The physical requirements relate to the environmental protection as well mechanical security. The methods used to terminate the cables vary according to the type of cable, type of connector and application. The common type of terminations are crimp connection, soldered connection, compression termination, and wire wrapping connection, direct connection, loop or eye connection. Some of the factors that determine the type are outdoor or indoor use, voltage, current, overhead, or underground, type of connector on the equipment where the cable will be connected. GIS configuration of joints. In GIS, these joints are represented as a simple point features connecting with electrical network lines. We have two different feature classes to represent the joints as LV joint and MV joint. In addition, we have the following subtypes in joints as per SEC. Underground straight joint, overhead straight joint, OHT joint, underground cap, overhead jumper, overhead line end, underground double branch joint, overhead double branch joint, overhead double branch joint, SR, underground double branch joint, SR, underground T-joint, shootout. GIS attributes for joints. We have to collect the following listed attributes for station from survey field and some attributes should be transferred from SEC mainframe/WMS/SAP database. Survey photos and attributes collected for joints. OH jumper, OH straight joint, OHT joint, OH double branch overhead line end. 18. Overhead lines. An overhead power line is a structure used in electric power transmission and distribution to transmit electrical energy along large distances. It consists of one or more conductors, commonly multiples of 3, suspended by towers or poles. Since most of the insulation is provided by air, overhead power lines are generally the lowest cost method of power transmission for large quantities of electric energy. GIS configuration of OH network. We have two major categories of overhead conductors based on their operating voltage, as MV OH cable and LV OH cable. Overhead conductor are represented as continuous linear network over the poles. These overhead lines, both the ends should be terminated/connected with a proper joint to make the proper network connectivity with other point features such as joints, cable risers, fuses, switches, ED service points and others. O cable digitization standards. OH cable needs to be digitized by connecting surveyed poles available in the database. If MV and LV conductors passing through the same pole, then MV line needs to be drawn over the poles and LV need to offset 0.2 meter from the MV line. OH lines should not be split at the poles except following two conditions. 1. When any attribute change occurs in the OH line. 2. When any OH line equipment placed over the pole 3. When OH joints are available in the network. GIS attributes for OH network lines. We have to collect the following listed attributes for station from survey field and some. Attributes should be transferred from SEC mainframe/WMS/SAP database. 19. Underground cables. An underground cable is a cable that is buried below the ground. They distribute electrical power. Such cables are an alternative to overhead cables, which are several meters above the ground. Overhead cables are often replaced with underground cables. Downtown areas with many tall buildings usually have few or no cables above ground. This is mainly for aesthetic purposes because underground cables cannot be seen. They are also less dangerous to people because they are out of the way. They cost more to install, but last longer. GIS configuration of UG network. We have two major categories of underground cables based on their operating voltage as MV-UG cable and LV-UG cable. Underground cables are represented as continuous linear network as per SEC UG digitization standards. These underground cable lines both. The end should be terminated/connected with a proper joint to make the proper network. Connectivity with other point features such as joints, cable risers, fuses, switches, ED. Service points and others. SEC UG cable offset standards. UG cable will be digitized by taking offset from parcel/row edge based on the street/row width. The offset between UG cables are always 0.25 meter. Between LV cables, 0.25 meter. Between MV cables, 0.25 meter. Between MV and LV cables, 0.25 meter. UG cable drawn from parcels should not cross the street center line. See below the different conditions for applying offset for UG cables. Case 1, street width is more than 10 meter. If the street width is more than 10 meter, first MV cable should be digitized at 5 meter far from parcel boundary. Additional MV cables needs to be digitized by maintaining 0.25 offset from first MV cable towards the street center line. Digitize first LV cable at 3 meter far from parcel boundary. Additional LV cables will be digitized next to first LV cable towards street center line up to first MV cable. If the number of LV cables are more and not enough space available between the first LV and MV cable, 3 to 5 meter space, utilize the spare area, between first LV and parcel to draw the additional cables. Refer the below depicted picture for the case of street width is more than 10 meters. Case 2, street width is less than 10 meter. If the street width is less than 10 meter, first MV-UG cable should be digitized at 0.25 m below the street center line. i.e., if the street width is 8 meter, then first MV-UG cable should draw at 3.75 meter, refer below figure. Additional MV cables needs to be digitized by maintaining 0.25 offset from first MV cable towards the parcel boundary. Digitize first LV cable 3 meter far from parcel boundary. Additional LV cables will be digitized next to first LV cable towards street center line up to first MV cable if space is available. If the number of LV cables are more and do not have enough space between the first LV and MV cable, then utilize the spare area, between first LV and parcel to draw additional cables. Note: when there is difference between as-built base map and latest base map, SEC recommended following the latest base map and drawing the lines accordingly. Crossing of cables are allowed when the connection bends are as per the internals of mini pillar and LVDB. Any new cable found from the latest as-built will be drawn down to the existing cable. These new cables are allowed to cross the existing cables. If the street width is 6 meter or less, draw the MV-UG cable first, below the street center line, if any, and then digitize the LV-UG cables below the MV-UG cables towards parcel boundary. If there is no MV-UG cable in a particular location, then start the LV-UG cable next to street center line. GIS attributes for UG cables. We have to collect the following listed attributes for station from survey field and some. Attributes should be transferred from SEC mainframe/WMS/SAP database. Attribute 20. Protective tubes. An electrical protective tube is a tube used to protect and route electrical wiring in a under roads crossing, building structure and other crossings. These electrical conduits may be made of metal, plastic, fiber, or fired clay. GIS configuration of protective tubes. We are using a polygon representation for protection tubes and we draw them to cover the full trace of the UG network crossing that particular location as depicted below. We have only one subtype as street crossing to represent the protective tubes. GIS attributes for protective tubes. We have to collect the following listed attributes for station from survey field and some attributes should be transferred from SEC mainframe/WMS/SAP database. 21. Meters. An electricity meter, electric meter, electrical meter, or energy meter is a device that measures the amount of electric energy consumed by a residence, a business, or an electrically powered device. Electric utilities use electric meters installed at customers' premises for billing purposes. They are typically calibrated in billing units, the most common one being the kilowatt-hour, kilowatt-hour. They are usually read once each billing period. Whole current meter CT meter. GIS configuration of meters. In GIS, meters are in table format, and to show the geographical location of the meter we have used the feature class service point, FCL_ed service point, and the same table information is linked through a relationship feature class as one many records along with relationship to OCL_customer. We have agreed with the below method of GIS representation for service points as per SEC standards. If the adjacent meter boxes are fed by same SOS, through interconnected cable between both the meter boxes, will be looped when there is a clear evidence from the photographs. Rules to be followed. 1. One EDS service point will be captured for each meter box. 2. Service connection cables will be drawn as per as-built maps for underground connections. 3. Service connection will be captured as per photographs for overhead connections. 4. Looping between adjacent EDS service points will be done with respect to photographs. 5. Do not loop when there is no clear evidence in the photographs. Examples: single EDS for single meter box, single EDS for double meter box, single EDS for quadruple meter box, multiple EDS at same location as per number of meter boxes available. In the below scenario, SEC recommended to K. Cable route identification and digitization rules. Digitize all underground cables as per the as-built drawings provided by using SEC UG digitization standards of offset. Local SEC will provide the missing EDS connectivity and routes, mostly as sketches. And the same will be captured in GIS within the delivery time. GIS attributes for meters. We have to collect the following listed attributes for station from survey field, and some attributes should be transferred from SEC mainframe/WMS/SAP database. Survey photos and attributes collected for meters. Double meter box. Quadruple meter box. 22. MV metering. MV metering is the large customer who consumes medium-level voltage directly from SEC, such as malls, schools, industries, other large consumers. GIS configuration of MV metering. In GIS we use energy meter to represent the MV metering with the combination of substation internals based on the real ground connectivity. Also had filled the OCL_meter attributes. GIS attributes for MV metering. We have to collect the following listed attributes for station from survey field, and some attributes should be transferred from SEC mainframe/WMS/SAP database. Survey photos and attributes collected for MV metering. The END